Hello everybody, let's start the second part of the chapter 9, this time with the derivation of the energy equation. This is the most difficult one to obtain, and you'll see why. We start with the equation 5.4 of chapter 8, which is this one. It's the energy conservation equation for each alpha species. And all we're going to do is to sum this equation over all alpha particles. In principle, it shouldn't be so difficult, but we have a few problems. So let's see. If you sum in alpha, then from the first term here, you get this 3/2 alpha del P alpha del T, right? Okay. The problem is you have this sum here, and it does not appear in the energy equation in the book. You don't know, it doesn't tell you what happened with this term. This term just disappears in the equation in the book. If you check equation number, let me see. So if you check equation 4.1 of chapter 9, after he has summed everything, you'll see that this term is missing. You don't have the sum of this term in the equation, and also you don't have the sum of the collisional term. And all he says in the book is that the collisional term vanishes when summed over all species of particles. But actually that would be enough for this term, but what happened to this one? So actually we have to guess what he did with it. So in practice, if you sum all the terms, including the first one based on equation 5.4 of chapter 8, you get, for summing the first one, you get 3/2 the derivative of pressure with time. Okay. So sum over all species. We have defined this quantity in this chapter, so the sum is just P. Now P can be written like this, using 1.14. 1.14 is like, let's check it. It's in the previous chapter, previous class of this chapter. We had 1.14. Where is it? It's here. Okay, so P can be written like this. We have done this in the previous video. So we have 3/2, the derivative with time of that quantity. It's 1/3 alpha. So I'm just copying that expression here. Let's call this equation star. And then we can cut this here. So it's based on 1.14. So in the right hand side of this equation 5.4 of chapter 8, you have the sum of this. So the sum of this is, if you use the definition of M, the collisional term given in chapter 8, it's this. It doesn't matter too much. It's just to make it more clear here. So we have this, and actually we are suppose that star is approximately equal to this. So actually both terms will disappear when you sum them, not just the last one. So if you sum them, if you have this approximation, then you end up with equation 4.1. Then you get from summing in alpha. The other terms in this equation will be the sum of alpha of del t 1, 2, and alpha v alpha plus the divergence of 1 over 2 rho m alpha v arrow alpha minus the sum of this last term f and this is equal to 0. So this is what remained from this. So we're summing the three terms, internal terms, and the other two are vanished. Okay, and here we are using in place of u alpha, I'm writing like this because we have already shown this, that and this is equation 6.2.1. we show this equation. Okay, all right, the question is, can we suppose that this is similar to this? If you compare the expressions, you'll see that this is del del t, this is delta delta t, and you have one half here of the sum of this times the average. This is an average in alpha as well. Sorry, it's an average in alpha. So both terms are pretty similar. Just here we're using this quantity here, where we know that C alpha 0 is actually V minus U. This is a fluctuation. This is from 1.8. So this is a fluctuation velocity, and this is the particle velocity. So, well, it's what is being adopted in this approximation. If you don't do this, it just doesn't. You don't get here. So you have to suppose that this is what he's actually considering. And when you sum over all alpha species, then this is similar to this. Okay, from 4.1, if you consider the first term, let's rewrite the first term in a way that will help us to continue. So, from the first term in 4.1, you get this. So I'm just repeating the term here, and if you use 1.8 here to for the definition of V, let's check it here. 1.8 is here. So let's use this expression for C alpha. So it's in terms of V, right? So V is C alpha plus U. So this using 1.8, we can write it like this. The sum in alpha of 1 over 2 will be C alpha plus U dot C alpha 0 plus U, this in alpha. There. Well, we just do the distributive here. Then you end up with this. I think I'll do it step by step. And if you think it's too boring, you can just skip this part of the video. but I'll do it anyway, just for the record. So, because this is so easy to miss the details, the steps. If you don't follow everything, things just don't make sense. So, distributing that product, we end up with this. Plus the final term. Okay, and then if we use the definition of C alpha H from 1.10, 1.10 is this. So C alpha H is, this one is like this plus this. So I'll do it like here. So everything again. And we have C alpha square plus 2. I'll write this using 1.10 like C alpha plus omega alpha. And alpha dot u. So here I used 1.10 plus, oh, this is just u square. You don't need the alpha because u is not a function of alpha, because u is already an average, so I don't need that sum. And then if you compute this average, here you have the average in alpha of C alpha, but then the average of C alpha, C is the fluctuation velocity. The average is actually 0, so because average of the fluctuation is 0. This is given in 622, so we can write 1/2 alpha plus this will be just like this, plus U2. Here I used chapter 6, expression 2.2, which says that the average is 0. Okay, so we are here. And now there's another step in the book. You go from here, and in the book you end up in this expression. This is on page, well, in my edition it's on page 225, just before equation 4.2, you have this expression here. It's derivative of in relation to t, derivative of alpha 1/2 rho m alpha c plus okay. Now the question is, how do you get from here to here? What happened to this term? Because here you have the first one, you have the last one here. What happened to what first? Why you're not summing? Well, you don't have to sum this here. You have already summed in the alpha particles. No, the sum of rho m alpha becomes rho m, and this times u2. You have this term here. So why is the sum of this equal to 0? This is a question mark for you. I have done it here, and it took me a few lines of algebra to show that this is actually 0. I'll leave it as an exercise for you. The book doesn't comment on this, but it's a nice exercise. So show what happened. Show what happened to this term. I'll leave it for you to think about it. And you will use, in the way to show it, use this. Omega alpha is equal to u alpha minus u. Then it should be clear after a few computations that you actually get this equal to 0, right? Well, then after this, you can use 1.14. Look at 1.14. 1.14 is this, so P is actually written like this. We have derived this in the previous class. So this P, where is P? Oh, okay, you can use this in terms of P. You can write like this. 1T 3 over 2 P. Okay? Plus the rest. Plus 1 over 2 rho m u square. And this is 4.2. Here I have used equation 1.14. Okay. Let's move on to the second term of 4.1. Remember, 4.1 is this. We have rewritten this term. Now let's move on to this one, the second term. For the second term of 4.1, we have, well, let's start with the rewriting this term here, which is part of the second term. It's not, the second term is more than this, but let's start rewriting this one. So this one is this, okay. V can be written like this. This is V square times V. Now, let's rewrite this by distributing this product to C alpha H dot U plus U square C plus U. Actually, I have just opened this square here. And this, well, I can rewrite it like this, or just, now I'll do the distributive. It's C alpha square, C alpha 0, plus C alpha 0 square, U, plus 2 C alpha 0 dot U, C alpha 0, plus 2 C alpha 0 dot U, U, plus U square C alpha 0 plus U square U. Okay, now using C alpha H is equal to C alpha, using C alpha 0 equal to C alpha plus omega alpha. This is 1.10, right? We have already used it before. And also this equal to 0, and this equal to this. This is actually, this is an equation 1.12 prime, what is it? 1.12, where is it? Okay, here. It's like here. Okay, this is equal to this. We have already shown this as well. So now this equation can be written like this. V is equal to C square arrow plus C this square u plus 2 c alpha naught c alpha naught dot u plus 2 omega alpha dot u plus u square omega alpha plus u square u. This is 4.3. Then we just have to take the divergence of this, because in equation 4.1 you have the divergence of the sum over the alpha species of 1 over this times this. This is actually the second term that we are rewriting. So I'll just put it like using this expression. You have the divergence of everything like there. Rho C. I'm sorry, this is really cumbersome, but if I don't do it like this, I will be lost in the derivation. So I cannot teach you anything if I don't open all these calculations. So okay, plus the other term, divergence of 1 over 2. Do we have all the terms already? No, because there's one more, and it doesn't fit here. It's divergence of the sum 1 over 2 alpha u square u. Okay, almost. So that's it. It's the final one. So this is equation 4.4. So we got it. Now, there is something missing here as well. If you noticed, I have written all these quantities, like this is here, this is here because it's square. This is here, again square. And where is this? Where is this? Why we don't have those two terms? I just have the final one. So another exercise for you. You're gonna do basically the same thing if you did it, you did here. Okay. So show why we don't have this and this term in this equation. The reason is the same. It's basically the same as in the previous one. So just do it. Open omega in function of u, rewrite it in function of u, and you'll see why these terms cancel each other, and you have 0 for them. All right. So basically, this is equation 4.4. Now let's use Q using the heat flux vector, total heat flux vector from 1.15. Where is 1.15? It's here, Q. You see that you have it here, right? You have it here. So using this and also the pressure tensor from 1.9. I'm not sure this. Oh, I'll do it. Let's do it. So where is 1.9? Oh, here. This is the pressure. It's also here. Where is the pressure? It's here. Okay. Then 4.4 becomes this divergence of the sum in alpha of 1 over 2 this is actually the divergence of the heat flux vector, total heat flux, divergence of pressure dot U, and the divergence of 3/2 P U, where here we have used 1.14, which is here, in place of P because it appears here. Okay, so pressure appears here again, scalar pressure, and we have another term, which is the divergence of 1/2 rho m u square u, which was this final term here, right? So this is 4.5. We got it. Not finished yet. We still need to deal with the third term. For the third term in 4.1, we have alpha and alpha f dot v alpha equals alpha and alpha q alpha, and well, this is just a set of external forces that we're going to add here, and then in place of F is the set of external forces, I'll use the Lorentz force and the gravitational force. So it's E plus, this is actually E, so it's strange. E arrow, V cross B plus gravity, then dot V, so dot V. And this is all in alpha average, right? Then we can write, and let's split this in terms. So we have NQE dot V for the first term. It's going to be N alpha times, well, N alpha is in every term, all right? So it's Q alpha E, E is an average, dot V. Plus, you have for the second term, it's Q V cross B dot V. So we have here V cross B dot V. But now here, V cross B is perpendicular to V, right? Because of the cross product. And perpendicular to V dot V is actually 0, because these are perpendicular. Plus the alpha G dot V. This is how 4.6 is written. Now we are going to use this identity from previous results, and also the fact that the average of the electric field is not is the same as E, because you don't have, it's not a function of alpha, so you can just write E here. So this is actually this, right? And the same for gravity. Then we end up with this expression here. It's equal to alpha and alpha Q alpha u alpha e plus alpha n alpha u alpha dot g. Well, by definition, this is the current density and times the electric field, and this is the mass current density, which was denoted by Jm in the previous video. So this is G. Okay, 4.7. Now let's combine 4.2. 4.2, 4.5. 4.2 is representing this, the first term. 4.5 is for the second term. We're going to use this. And 4.7 for the third term. Into 4.1 using 4.2, 4.5, and 4.7 in 4.1. You obtain the derivative of 3p over 2 plus the divergence of 3 over 2 p u plus derivative of 1/2 rho m u square plus divergence of mu square u plus divergence of g plus divergence of pressure dot u minus j dot e minus jm dot g. This is equal to 0, equation 4.8. We still need to do a few arrangements. If you check the terms 3 and 4, this is the derivative of a product of functions of t. So and the same for the divergence. We can use the product rule of derivatives. The derivative of a product is like a derivative of this times this, and this times the derivative of this. So for the third and fourth terms, we can write them like this: 1/2 rho m1 square plus divergence of 1/2 rho m u arrow is equal to 1/2 u square divergence of derivative of this plus this. Why am I doing this? You'll see in a moment why this is beautiful. Rho m del u del t plus u dot divergence of u. This is 4.9. Now, we have already seen that this is actually du dt, right? With capital D. We have defined this derivative, material derivative like this. Okay. Then we can use 2.2. Let me see if I find 2.2. Okay, in 2.2 we have the continuity equation, right? The continuity equation says that this quantity is equal to 0. Okay, this quantity is here. So this is actually 0, right? So this is good. Let's do it in another color. This whole term is 0 because of 2.2. And we have this term here. From 3.7, well, this is rho m times this. 3.7 SAS. 3.7. Where is it? 3.7. See, rho m times du dt is equal to this. So we can use this expression in place of this. So using 3.7 for rho m du dt. Oh, actually, arrow here. 4.9 becomes equal to the, let's just write the right hand side here, okay? This right hand side is equal to rho u dot e plus u dot j cross b plus jm dot g minus u dot divergence of p. Now using 4.10 in 4.8, remember 4.8 is this, we get d dt 3p over 2 plus 3p over 2 divergence of u plus divergence of q plus p dot nabla dot u equal to j dot e minus u dot j cross b minus rho u dot e. 411. But there is more we can do. It's not finished yet. Note that J is actually defined as N alpha Q alpha U alpha, which, using the definition of omega, we can, in terms of U, you can write it like this: omega alpha plus U N U Q alpha U. And we'll call this J prime plus rho U. Okay, so this is a rho, the density, and this will be called the J prime. And also, we can rewrite this term as minus J dot U cross B, which is, well, J, I can write it using J prime, so it's minus J prime plus rho U dot U B. So sorry, I forgot to point that this is J prime. Okay, what else? This one can be written like this: minus J prime dot U cross B minus rho U dot U cross B again. U cross B is perpendicular to U, so the dot product with U is 0, right? Okay, 4.13. Now we're going to use 4.13 and 4.12 into 4.11. You have this term and this. Using 4.13 and 4.12 in 4.11, we get d dt 3p over 2 plus 3p over 2 divergence of u plus divergence of q plus p dot nabla dot u is equal to j prime plus rho u dot e minus j prime dot u cross b minus rho u dot e. And now it becomes clear why I have done this, because here I can just cut this with this. And so we have simplified it to j prime dot e plus u cross b, which we can call, this is arrow, we can call j prime dot e prime. I'm calling this e prime, okay? 4.14, where e prime equal to e plus u cross b is the electric field in a frame moving with velocity v. Velocity v. Okay, here we have it. Let's just write the final version. Therefore, finally, d dt 3p over 2 plus 3 over 2p nabla u plus divergence of q plus pressure nabla dot u is equal to j prime dot e prime. This is our energy equation. You have here in the first term, it's just saying that the rate of change of the energy density, total thermal energy density, is a function of the other terms. The second term is the thermal energy transfer to the volume by particle motions given by this velocity, divergence of the velocity. So this is a contribution of those particle motions to the change of the energy. You have the contribution of the heat flow. You have the contribution of the pressure here. And you have the Joule heating. This is called Joule heating. Sometimes ohmic heating. Ohmic heating. Or also resistive heating. Both names for the same thing. Resistive heating. the heat production due to the passage of electric current by a conductor. So you know these terms from physics in other contexts maybe. This is our Joule heating. Then, from now, we can think about the electrodynamics of a conducting fluid. That is section 5. Section 5, electrodynamics of 4, I don't know, 4. A conducting fluid. You see, we have derived the continuity equation, the movement equation, energy equation, but for each equation there are always some new variables that need to be computed, that you need an equation for them, because if you check this equation 4.14, we have the equation for P, small p, but then you have capital P. This is a tensor. We don't have an equation for this. We must write an equation for P. And this equation will need the triad tensor for the heat flow, total heat flow, and so on and so forth. And we also need an equation for the heat flux vector. Then there's always a new equation that needs to be derived. We have to truncate this procedure at some point. So if you decide to truncate it here, to stop here, then you will need an equation for the pressure. Well, let's see what we can do from here. So we'll try to simplify things. We cannot just go on forever. As we are now, we need an equation for the electric field, the magnetic field, the current density, and the charge density at least. Then we think about pressure. So let's start with Maxwell's equations. We have Maxwell for the rescue equations. Okay. Then we have from him the curl of E is equal to minus del B del T. That's Faraday's law, right? We have Faraday's law, and we have Ampere's law, which is the curl of B equal to mu naught times J plus epsilon naught del E del T. So if you solve both equations together, so you have a coupled system for E and B, two equations and two unknowns. So we can find the electric and magnetic fields from these equations. Now we have also the conservation of charge, or charge conservation. So for this, you have to start with equation 3. If you multiply equation 8.3.2, this is from chapter 8. I have not recorded a video from chapter 8. This is from Professor Flavia, but you will remember this equation if you multiply it by Q alpha over M alpha and sum in alpha, then you obtain this equation. You're summing over alpha particles plus the divergence of this quantity is equal to the sum in alpha for collisional term. And they suppose that the sum of the collisional term is 0 because it shouldn't affect the total electric charge. So suppose this is 0. There's always something like that. We don't always understand precisely why they suppose this, but it's the way it is. Otherwise, you can't simplify things, right? And you end up with this because this is the current density and this is the current density. Sorry, current density is this. This is charge density. Sorry, this is charge density and this is current density. Okay, so if you take the divergence of 5.1, whereas 5.1 is this. So taking the divergence, of 5.1, you get divergence of curl of E. Divergence of a curl is always 0, right? So we get rid of this term, minus del T of the curl of B. So since this is 0, we have also if the time derivative of the divergence of B is 0, then it means that the divergence of B is constant. Of course, if you start with divergence of B equal to 0, which is the Gauss law, then it will stay 0 forever. So that's what we mean. Since, let's say, if, because you may think physically, of course, divergence of B is always 0, because we know that. But your computer does not know that, so you need to tell it that it's constant. So it's solving the equations, and then if the equation if the divergence of B is equal to 0, if this is equal to 0 in the initial condition, then divergence of B is equal to 0 forever because of this. So Gauss law will not be affected, will not be disrespected. And in section 5.3, there is a derivation of the generalized Ohm's law. This is a fairly long section, but it's not difficult to understand. There are no tricks, there are no magics performed. I don't have to show you any hidden motions in the derivations. So I think you may just read it, okay? Read it in the book. But then you will have the derivation of this equation here. J(T) minus 1 over N E, divergence of electron pressure is equal to electric field plus U plus B, sorry, this is U cross B, minus 1 over N E J cross B minus 1 over conductivity J. Okay, so at some point you will see that in the book you end up at equation 5.35. PE, as I said, is the electron pressure. is the pressure performed by the electrons. If you have a plasma with only two species, you have electrons and one type of ion. That's the type of plasma which is considered in this derivation. Usually we consider that the electron mass is much smaller than this term here. Okay, so this is much smaller than n, the density, times the charge square. So usually electron mass is very small, right? And also usually this and this is small, so that you can get rid of this first term here, and so is the divergence of pressure. You see, this is much larger than this. You can remove both terms. Then 535 becomes J equal to conductivity, this minus this J cross B. Okay, we have kept this and these terms, so these are zero. This final term is the whole term. This is a simplification of the generalized Ohm's law. You can do even simpler than this. Sometimes the whole term is dropped. This may be considered when you have sigma times the modulus of B much smaller than this. So if you think the modulus of the upper term is smaller than this, which is true when you have a highly collisional plasma. In a highly collisional plasma, the number of electrons is very large. So you have here the number, density plus times the electric charge. So this term is in a highly collisional plasma is much larger than this. So in these cases, you may drop the whole term. The whole term may be dropped in highly collisional plasmas. Then you end up with this form of the Ohm's law equation for J in terms of just E and U cross B. Yeah, just drop this one. If you don't have an external background field, magnetic field, then all you have is if B is equal to 0, then J, I added a 0 here, we don't need it. Okay, J is just this. You know this, it's Ohm's law. And from here we can think about a set of simplified MHD equations. Simplified MHD. Which equations will we use? Let me see, we have 2.3, where is 2.3? Let me find them. 2.3. No, it's in this previous class. So 2.3. We start with this. Okay, have a continuity equation here. 3.7. 3.7 is, where Where is it? Here. Okay, equation of motion. Then 414. Energy equation. Then we have 5.1. 5.1, where is it? 5.1 here. 5.1, 5.2, 5.4, and 535 here. Okay. Okay, of course, we can use the simplifications that we have thought of. So in 5.2, what are you going to do here? We drop this term. This is a fairly standard way of representing this equation, Maxwell equation, without this term. In the book, he says that dimensional analysis shows that this term should not be dropped, but in fact, usually it is. You think in collision of plasmas, you think about terms that are slowly changing in the electric field. You have a slowly changing electric field, so this time derivative is usually dropped. But some people may complain that it is not accurate, physically accurate. Then we keep 5.4 and 535. But well, let me see what else we can do. In 5.4, let's think about 5.4. We have divergence of J. If you have the electric density null due to quasi-neutrality of the plasma, because if you have quasi-neutrality, this is charge density, electric density, right? So it should not be changing with time. You have it 0, so the time derivative is 0. If the time derivative is 0, then the divergence of J must be 0. And if divergence of J is 0, then in 3.7 we lose the electric field. Where is it? In 3.7 we drop the electric field in the equation of momentum, right? Then there is another thing about equation 536. Equation 530, oops, 36, this one. Okay, even this may be used instead of this, or sometimes you drop the whole term and you may use 37. And also we do not consider viscosity and thermal conductivity. So we don't need the heat flux vector, and we don't need the pressure diet. The pressure diet becomes a scalar pressure if you drop viscosity and heat conductivity. So doing this, we have the following set of simplified equations. We have the mass density, given by this. In terms of velocity, then for velocity we use this form of the momentum equation or equation of motion, just with J cross B. And the scalar pressure, there is no heat flux, there is no not heat flux, there is no gravity here. Gravity is not being considered. Then we have, well, we need an equation for pressure. You have a scalar pressure here, and the equation for pressure is given by the equation of state, the state equation of adiabatic plasma. I have mentioned this in the beginning of chapter 9. This is state equation. Actually adiabatic, right? Adiabatic, no heat flux. Adiabatic state equation, where you have gamma given by n plus 2 over n, where n is the dimension of space. It's usually either 2 or 3, right? If you have in 3 dimensions your simulation. Then we keep Maxwell's equations without displacement current. This is 6.7. And then we have equation for B, just in terms of J. And Ohm's law. Simplified Ohm's law. Oh, include the whole term here, but usually it's not used in the most simplified form. So this is whole, and sometimes this is equal to 0. Okay, it's considered, it's dropped from the equations. If we consider that conductivity is infinite, this is a particular case, another simplification. If conductivity is infinite, then 6.10 becomes 6.10. We use, okay, this, we'll drop this, and you consider just this part, and we'll divide by conductivity. You have J over this, E plus U cross B. Then you can obtain the electric field, if you want, just from this. And then you have ideal MHD. Ideal means infinite conductivity, no resistivity. Okay, and I think finally this is the end of chapter 9. See you next time in chapter 10.